Hello. We are going to take a 20 question test based on the videos 1.1 through 1.7. So I admit that this test might be a little bit challenging, but look on the bright side. If you're able to do this test and answer most of the problems correctly, then you're good to go. You've got all the concepts down and you're golden. So let's work on number 1 through 20 together in this video. So to start off, we are going to do number 1. Name the states of matter found in this sample of nitrogen. Now, what do I mean by nitrogen? Well, it's this stuff and this stuff. Basically the liquid that you see. And I basically just told you the answer. That does not have a definite shape, but it has definite volume. So it's a liquid. And down here we have some clouds that are forming because nitrogen likes to exist as a gas and not a liquid. So that's why it's starting to evaporate all of a sudden. So that's a gas. So that's our answer. The states of matter found in this sample of nitrogen is, well, it's liquid form and it's gaseous form once you pour it out. So let's move on to the next question. Number 2, what type of solid is this? Is it a crystalline solid or an amorphous solid? Well, in a crystalline solid, the atoms or particles are arranged in an orderly state, while in an amorphous solid, the atoms are arranged in a less orderly state and tend to be less stable or less sturdy than crystalline solids. So in the video from one of the lessons, we learned that an amorphous solid includes butter, which is soft and very squishy. And the example that I gave for a crystalline solid was an emerald, which has atoms arranged in orderly states, which is responsible for the sturdiness of emerald. So in this image, these atoms look very orderly. They are arranged kind of, very consistently. They have this nice little pattern going on. They are in straight lines, in straight rows and columns. So I think this is a crystalline solid, A. Number 3, O stands for the element oxygen. This is the atomic structure for ozone, which is, I'm presuming, a molecule. Ozone is a or an element, molecule, compound, atom, or crystal. So we have to figure this out. So this structure right here has 3 oxygen atoms shown here. And don't worry about these plus signs and these minus signs or these angle measures or these length measures, because those are, I guess, extra information that you don't need to solve this problem. We are just looking at the atoms. So there are 3 oxygen atoms, so we can write this as O3. Now, is ozone an element? Well, I don't think so, because an element is just a type of atom, and this picture clearly does not show an atom. It shows 3 atoms stuck together, so this is not an element. Now, we can immediately cross out D, because we know this is not an atom. Ozone is not an atom, because there are multiple atoms stuck together, not just one. So, is it a crystal? Well, there's only one of it, and remember, in crystals, like crystalline solids, the atoms are arranged in an orderly fashion, and there are usually a lot of them, like in the last problem. So this is not a crystal. And we have 2 options left, molecule or compound. So a compound has multiple elements, aka 2 or more elements, inside the structure. But clearly we only see oxygen atoms being incorporated into ozone. So this is not a compound. Now, the definition of a molecule is just a substance with 2 or more atoms. This clearly has 3 atoms, which is more than 1, so we can conclude that the answer for this is B. Ozone is a molecule. Next question. A mixture of iron metal, insoluble meaning not dissolvable, nickel 2 sulfide, and ice are present in Jason's backpack in super small microscopic pieces, which just means that they're super duper tiny. So let's read on. How would he separate these 3 if the melting point of iron and nickel 2 sulfide is much greater than the melting point of ice? So how do we figure this out? Well, why don't we just draw it? So let's say iron metal is in red. Let's draw some iron metal. Let's draw some insoluble nickel 2 sulfide in blue. And let's draw the ice in yellow. So I know it's not very intuitive, the colors don't match, but what can I do? So let's figure this out. Let's read A. Melt the ice into a bucket and sort the other substances with hand. Well, if I melt the ice into the bucket, then the ice will be separated from the mixture. So ice in this picture is yellow, so we will cross them out because we separated them. Now the next part says sort the other 2 with hand. But how is that possible? We just established that these particles are in super small microscopic pieces. So it is impossible to separate these by hand. It would take a very long time and it would not be practical. So A is out of the picture. So let me undo this for a second. So A is out of the picture. Let's look at B. Melt the entire mixture with a Bunsen burner so it becomes a liquid. So essentially what this is saying is that this entire mixture will turn into a liquid. Now does this really help us separate it? Well, not really. So that's wrong. So let me just undo this once again and cross out B. C. Melt the ice into a bucket and use a magnet to take out the iron. Now we're talking. So if we melt the ice into a bucket, we are effectively separating the ice, and thus we can cross that out. And if we use a magnet to take out the iron, we take out the iron, which is in red, and we're left with the nickel 2 sulfide. So we've effectively separated the ice and the iron, and we leave the nickel 2 sulfide. So we separated the 3 apart from each other. So I think C is an amazing answer. So let me just undo this and say C is our answer. Now let's look at D, just for the sake of learning. So put the mixture in water. Well, if we put the mixture in water, like let's just say this got submerged in water, so the ice will melt in water, because if you put ice in water, it will melt over time because of the temperature outside. But we are left with some iron metal and some nickel 2 sulfide. And remember, they are still inside the water, and nickel 2 sulfide is not dissolvable in water, so it'll stay there, and iron, based on common sense, will not dissolve in water, because you can try it yourself. Take a metal spoon, put it in water. Will it dissolve? Nope. So these 2 will stay in the water, and they will not be separated, so thus you have failed your task. So D is not a correct answer. So let's move on to number 5. Now this one comes from the ACS, and what I mean by ACS, well, it's called the American Chemical Society, and they have these questions from the Chemistry Olympiad that are challenging, and that's why I want to put it in this video, because I want to challenge you guys a bit. So before we look at the question, I am here to give you a hint, because you might have not known some of this stuff. So air has a density of 0.00128 grams per milliliter, water has a density of 1.00, mercury 13.6, ice 0.93, aluminum 2.7, and gold 19.3. Now, what trend can we see from this? Well, we can see right off the bat that air is super low in density. But what about liquids and solids? Well, in liquids, we can see that the density can vary from 1 all the way to 13.6, while for solids, they can vary from 0.93 to 19.3. So my question to you is the density a good indicator of the state? Well, the answer is yes and no. If we have a density like 0.0013, we can most likely assume this is a gas, since gases tend to have densities that are less than 1 or 0.1. Now, what if I gave you another density? So what if I said that the density of an object was, hey, look at that, 3.12. Can you conclude that the substance, this mystery substance with a density of 3.12 grams per milliliter, will be a liquid or a solid? Well, this could either fall here or here. So as a result, you cannot tell whether something is a liquid or a solid based on the density of 3.12. So now let's read the problem. Number 5, an unknown substance is not easily compressible at high pressures and has a density of 3.12 grams per milliliter. This substance is most likely A. Well, we established that it cannot be a gas, since gases usually have densities that are less than 1. Now what about B, C, and D? Well, we know that we can't distinguish between a liquid or a solid solely based on 3.12. But what about the other description? It says the substance is not easily compressible at high pressures. Now, from a video I did about the states of matter, I told you that solids and liquids have a constant volume. So let me write that, a constant volume. So this applies to solids and liquids. And I told you that if they are exposed to high pressures, the volume will change, but it will change very, very slightly. So we essentially assume that the volume is constant because the change in volume under high pressures is so small that it is negligible, or aka we don't care about it. So does this fit the description of not easily compressible at high pressures? So yeah, both solids and liquids are not easily compressible at high pressures because they like to have their volume kept constant. So therefore, both of these descriptions are not sufficient enough for us to differentiate between liquid and solid. So therefore, C is our answer. So this is one of the harder problems, but we got through it as a team, and if we can get through hard problems like this, we can get through hard problems any day. So let's look at number 6. Ooh, it's another multiple choice. Magnetism is an... Oh, I just wrote and because the answers start with the I or E. Huh, interesting. So what is magnetism? Well, magnetism is the ability of a substance to be attracted to a magnet. So if you're attracted to the magnet, then you exhibit magnetism. To be more technical, anything that releases a magnetic field, like this one, for example, although it's not fully drawn, anything that produces a magnetic field can attract or repel other objects that have their own magnetic field. Now, I won't go too deep into the concept, but what you need to know is that magnetic objects repel or attract other magnetic objects. So let's get back to this. Magnetism is what type of property? Well, is it an intensive or extensive property? Well, intensive properties are properties that don't depend on the amount, and extensive properties are properties that depend on the amount. Now, if you have a little bit of magnetic object versus a lot of magnetic object, aren't both of these still considered magnetic because they exhibit magnetism? So for that reason, it doesn't matter what the size of it is, both of them exhibit magnetism, so we know that C and D are out, and we're left with A and B. Now, is this a chemical or a physical property? So in order to answer that question, you have to ask yourself, when an object is magnetic, is it changing into another substance? Well, not really. A magnet, like, I'll draw another magnet here, just attracts, paper clips and such without having to change its composition, because the magnet is still a magnet, so it's not a chemical property, but it's actually a physical property because you aren't changing the composition, so it is not a chemical property, so the answer is B. Now let's look at number 7. Which of the following is not an example of separating a liquid containing mixture? So liquid containing mixture would just, have liquid and have some other stuff in it, maybe stuff that's dissolved in it, or maybe instead of stuff dissolved in it, we might have some suspensions that can easily be separated by filtration. So which of the following is not an example of separating a liquid containing mixture? Well, we know that both types of distillation separate the solute from the solvent by evaporating the solvent mixture into the air and through a tube and to the receiving flask. So A and B are out. What about filtration? Well, we use filtrations when we have a suspension containing a liquid and some large particles. So for example, these red particles can be separated from the purple liquid by filtration. So you might set a filtration device like this, and you might have some filter paper that separates the suspensions, and once you filter it out, the purple liquid will pass right through, while your red pieces of, whatever they are, stay stuck to the filter paper, so they're separated. So C is out of the picture because filtration allows you to separate liquid containing mixtures. Now, D we didn't talk about, but judging from what we determined by crossing out A, B, and C, then the answer must be D. So a good trick to doing multiple choice test is to cross out every other answer that is wrong and leaving yourself with one answer that is most likely correct, even though you don't know what it means. So let's move on to number 8. So for this question, you obviously need a calculator for this, unless you want to do everything by hand. I mean, it's up to you, of course. So let's read this question. 1 carat has a mass of 2.00 times 10 to the second milligrams. So let's write our conversion factor right here. So 2.00 times 10 to the second milligrams per carat. And you might be wondering, why don't I write 1 carat? Well, here's a little secret. When you're writing conversion factors out as a fraction, you usually never include the 1. You only focus on the number that's not 1, which is 2.00 times 10 to the second. And as a result, you only focus on this number, so that's the number that will determine the number of sig figs, and not this 1. So we just leave it as invisible in order to not count that as part of our sig figs. But 2.00 times 10 to the second milligrams per carat is an exact number, so we don't have to worry about sig figs because this has an infinite number of sig figs. I just want to clarify the 1 here and say that you do not count that as a part of your sig figs whenever it's a part of a conversion factor. So let me erase this. This is going to take like a few more seconds. Alright, so let's rewrite that in a smaller text. 2.00 times 10 to the second mg per carat. And it says diamonds have a density of 3.51 grams per cubic centimeter. 3.51 g per cubic centimeter. So I don't write the 1 once again because we pretend it's invisible because it doesn't count toward our sig figs. Now, in the description for video 1.7, I wrote about how one could tell the difference between an exact number and something that's not an exact number. So something that's artificially, I guess, determined by scientists in order to set a standard, like for example 2.00 times 10 to the second milligrams are in 1 carat. That's something that we people set as a standard, which is why it is an exact number. Now, what about this? This is density, and density is something that is measured. So as a result, something that you measure is not infinitely precise. It is only as precise as the instrument you use. So therefore, conversion factors that are measured, like density, since we measure density, is a number that is not an exact number. This number will have a limited number of sig figs. So it will have a number of sig figs. So now that we got that out of the way, we will now continue the problem once I undo everything. So I need to undo all these red lines. So I need to erase that. And let's read on. How many cubic centimeters are in a 5 carat diamond? So our objective is to convert 5 carats to cubic centimeters. So how do we go about that? Let me undo this. So let's start off by just writing 5 carats. And let's multiply this by conversion factor in order to get us closer to cubic centimeters. So we have to think of like a roadmap. So we can go from carats to milligrams, hopefully milligrams to grams, and then grams to cubic centimeters. That would be a very efficient roadway in order to get to our answer. So I am going to do that. So let's multiply 5 carats by the conversion factor here. So if we want carats to cancel out, we will put carats on the bottom. So carat on the bottom, and on the top we will put 2.00 times 10 to the second mg. So when I do these conversion problems, I like to keep the numbers there and simplify it all at the end. So let's just continue this process. So if we want to convert milligrams to grams, we have to multiply by a conversion factor. Well, I know that a milligram is equal to 10 to the negative third grams. That's another conversion factor. And we have grams now because these carats canceled out and these milligrams canceled out. So we have grams. Now we need one more step, which is over here to convert grams to cubic centimeters. So let's just multiply by that. So we want grams on the bottom, so 3.51 grams, and cubic centimeters on the top. And our grams will cancel out, and we will be left with cubic centimeters. So all our units cancel out. That's amazing. Now let's combine our answer. So we are doing basically this. 5. Well, let's do a different color. I'm going to do it in, how about yellow? 5 times 2.00 times 10 to the second, let me put a parentheses around that, times 10 to the negative third, and then divide that all by 3.51. Because if you're multiplying by 1 over 3.51, you're essentially just dividing by 3.51. These two are exactly the same thing in terms of meaning. So let me undo that. And let's solve this problem now. So let's start off from left to right. So 5 times this number will get us 1 times 10 to the 3rd power. And why do I have 1 sig fig? Well, because 5 has 1 sig fig, and this is an exact number because it is a conversion factor that is determined by us humans, so therefore the lesser of the two is just 1 sig fig. So this answer will have 1 sig fig, as shown here. Now we are going to multiply by 10 to the negative 3. And remember that this is also an exact number, so it has an infinite number of sig figs, so we are going to look at the lesser of the two. So we have 1 times 10 to the 3rd, and we have 10 to the negative 3. So the lesser of the two is just 1 sig fig, and we get 1 as our answer. And our last operation, after doing this operation and this operation, is to divide by 3.51. So 1 divided by 3.51 is equal to about 0.3. And I keep 1 sig fig because the top simplified to 1, which has 1 sig fig, and the bottom simplified to 3.51. So we have 0.3, and we need to put units on it. So our units just comes from here because this is the only unit that didn't get canceled out. So our final answer is just 0.3 cubic centimeters. That wasn't so bad. Let's go on to the next question. What type of mixture is this? Well, looking at this, I see some water and I see some white powder. So they are clearly distinct and they seem like they're easily separable. So as a result, I think the answer is a suspension. It is not an alloy because it is not a mix of two metals. It is not a solution because I can easily tell the difference between the two components. And it is not a colloid because the particles are not small to the point where I can't see them. In fact, I could clearly see them right there. I could clearly see the chunks in there, and you know, it's not distributed like evenly throughout the solution like a colloid would be. Instead, it's just all resting on the bottom, as in this picture, and that eliminates it as a colloid. So, next question. A scientist has a homogeneous mixture which is composed of two liquids with similar boiling points. Which method or apparatus, aka a tool or setup, should be used to separate the two liquids? So, I imagine a homogeneous liquid would just be a liquid with, you know, two separate liquids in it, but they are mixed so well that they appear to just be one liquid. So you want to separate them, and they have similar boiling points. Would we use a separatory funnel? Well, if you remember, a separatory funnel kind of looks like this, and then there's like this little valve that opens and closes, and usually we use this when there are two distinct liquid layers. I'm going to use a different color. That's kind of confusing. I'm going to use yellow. And this over here is a solution, aka a homogeneous mixture. So we can't really separate it into two different layers since it's all mixed. So a separatory funnel would be out of the picture. Filtration, well, we can only use filtration if we have a liquid and some solid particles that can be separated by filtering it through a filter. And since it's a homogeneous mixture, we cannot do that. And for simple distillation, we use simple distillations when we are separating things with high boiling point differences, so that's out of the picture. Now, fractional distillation makes a lot of sense since we separate homogeneous mixtures that have similar boiling points for its components using fractional distillation. So I think that's the correct answer for this one. So let's now look at our next question. What is 101 Kelvin in degrees Celsius? Well, in one of the videos, I said that a Kelvin is equal to a degree Celsius plus 273.15. So this is just simple math. 101 is equal to degrees Celsius plus 273.15. and then you'll subtract 273.15 from both sides. So 101 minus 273.15 is equal to degrees Celsius. And we have to make sure to keep track of our sig figs. So when you're subtracting, you are going to look at the decimal places, and since this has 0 decimal places and this has 2 decimal places, our final answer will have 0 decimal places. So let me type this into my calculator. 101 minus 273.15 gives me negative 172.15, but since we want 0 decimal places, then our final answer is just negative 172 degrees Celsius. Now let's look at number 12. How many centigrams are there in 1.23 times 10 to the 5th kilograms? So let me just clear the ink on the page in order to show that. Let's write our previous answer here, 172 degrees Celsius. Now let's try to solve this problem. So this is another case of conversions between different units. So let's start off with 1.23 times 10 to the 5th kilograms. So we are going to multiply that by our conversion factor with kilograms on the bottom, and on the top we know that 10 to the 3rd grams are in a kilogram. So our kilograms cancel out, and now we need to convert grams to centigrams. So we know that 10 to the negative 2 grams is equal to 1 centigram. So we have our grams cancel out, and we are left with the unit centigrams, which is what we want. So now let's just multiply the numbers together. So 1.23 times 10 to the 5th times 10 to the 3rd will give me 1.23 times 10 to the 8, and then we have to divide by 10 to the negative 2, which will give us 1.23 times 10 to the 10 centigrams as our final answer. So let me just erase all that. I'm going to clear the ink. So our answer is 1.23 times 10 to the 10 centigrams. And this answer was negative 172 degrees Celsius. So notice how I just kept the number of sig figs, which was 3, consistent, because all the numbers or conversion factors that I multiplied by were exact numbers, so I just ignored the sig figs on those. Let's look at number 13. Micro is 10 to the negative 6. That's just something you memorize. How many sig figs are there in this number? So let's count. We have 4 here, so we're going to count from left to right. So 4, and then we have 5, 6, 7, 8, 9, 10, 11, 12. So we have 12 sig figs here. And we count these zeros here because, remember, the decimal place is a green light to count all the zeros after the first non-zero digit, which was this person right here. So we get to count everything, even the zeros. So there are 12, right? Let me double check. Yeah, there are 12. All right, let's go on now. So this is an algebraic problem with consistent sig figs. So we have to give an answer in consistent sig figs. But we have to do this based on order of operations. So we are going to use PEMDAS for this. So let's start off by looking at this for a second. We have to do the parentheses first, as indicated by the letter P in PEMDAS, which tells us the order in which we should do the operations. So let's do our first operation, this person right here. I don't know why I call numbers people, but I just like doing that. So we have to do this right here. So let's just subtract them. 6.023 minus 1.2 will give me 4.823, but since this has 1 decimal place and this has 3 decimal places, we want to stick to 1 decimal place, so this will be 4.8. But for the sake of accuracy, we will keep the 2, 3, and we will mark the first decimal place with a red line in order to remind us that this number has one decimal place. So let's simplify log 10.0. So if I typed log 10.0, I get number 1. But I don't think that's right. Not exactly right. So we'll get 1, of course. But we have to remember our significant figures and the rules. If we take the log of a number with 3 sig figs, our answer will have 3 decimal places. So we have to make it so that 1 has 3 decimal places. So just simply add 3 zeros after. And therefore we have 4 sig figs here and 2 sig figs here. So now let's look at our next order of operations that we have to do. Well, it seems like we only have division and multiplication left, which are equivalent on the PEMDAS acronym. So let's just look from left to right. So we have to multiply this by this. So let's just type that in. 3.0122 times 4.823. And I get an answer of 14.528. So we need to make sure that our sig figs are accounted for. Remember, this number has 2 sig figs because I underlined the 8, which is the first decimal place. And this number right here has 5 sig figs. So we have to choose the lesser of the two, and thus our final answer for this will be kept at 2 sig figs, which will be located right there. So now our last step is to do division, and we have to divide by 1.000. So this has 2 sig figs, this has 4 sig figs, and anything divided by 1 is just the same thing. So our final answer will have 2 sig figs, so it will be 15. And that's because 5 over here rounds up. So this number will be 5 instead of 4, and that's why our answer will be 15. So let's look at the next question now. Use the left-hand side, which shows degrees Celsius. Ash, a Pokemon character, wants to measure the temperature for one of his experiments. According to the thermometer, which is that thing, what should Ash write on his lab report, assuming that he can go 1 extra sig fig past what he is 100% certain about? Well, we have to read the left-hand side, so let's just ignore the right-hand side. And let's figure this out. So the thermometer reading will be right there, and it looks like it'll go about right there. So we have to figure out what that is. So that's 20 and that's 30, and it looks like there are a total of 10 tick marks, because if you think about it, if that's 20, then that's 21, 22, 23, 24, 25, 26, 27, 28, 29, and 30. So each, I guess, unit counts as 1. So this yellow line represents, what the reading was, and it seems like it hit 22. So we can be for sure that it's going to be 22. Now, that's what we're certain about, but can we kind of estimate a little further? Well, yes. So let me erase this to be more clear. We can clearly see that this marking is like a little above 22. Because I don't know how to explain it, but you just see that it's a little above 22. So we are certain that it's above 22, but we're not sure what the 10th digit is. So we can estimate this since we can go 1 extra sig fig. So I'm going to say it's 22.1 degrees Celsius, and that's our final answer. Next question. In chemistry, this is a rate law. Rate equals K times the concentration of A squared. Don't worry about what they're called, just worry about how to find the units, which is the point of this question. So our rate can be written as moles over liters times seconds, and we set that equal to K, which is the unit we want to find. times A squared. So A is just moles per liter squared. And we have to now kind of simplify it. So we gotta use a little bit of algebra. So moles over liter times second is equal to K times mole squared over liter squared. So we want to isolate the K in order to find its units. So let's multiply both sides by mole square over liter squared. So let's multiply the same thing on both sides in order to cancel these two out. So we determined from this that K is equal to liter squared times mole over mole squared times liters times seconds. So now we could start canceling out some stuff. So the liter will cancel out, leaving this with a 1. And the mole on the top will cancel out, leaving this with a 1. So let me rewrite this in green. So K will be equal to, it seems like liters over moles times seconds. And that is our final answer. So now let's move on to number 18. Iodine solid sublimes goes from a solid, wow, that's a bad cube, to a gas. So what is the change? So what type of change is this? And does iodine lose or gain heat when it sublimes? So let's think about this. Changing states is a physical change, so C and D are out. And when you go from a solid to a gas, you are gaining energy because remember, the order of, the amount of energy inside the states goes as follows, from solid to liquid to gas to plasma. So that's the highest energy and that's the lowest energy. So if you go from a solid to a gas, you are gaining energy because you are going from a lower energy state to a higher energy state. So I'd say that the answer to this question is A. So now let's go on to the next question. Chemical A is a solid that weighs 15 grams. So let's write chemical A is 15.00 grams. When chemical A decomposes and breaks apart, the following reaction occurs. So we see that A is transforming into B and C, as indicated by the arrow. So it says after the reaction, so this is before and this is after. So after the reaction, 3 grams of chemical A, so we have less of chemical A, we have only 3 grams left, and 5 grams of chemical B. So let's write 5 grams of chemical B are measured with a scale. Chemical C escapes into the atmosphere since it is a gas. So as you can see here, C is a gas, A and B are both solids, so we can measure them. But you can't really measure the mass of the gas if it runs away from you and escapes into the atmosphere, right? So what is the mass of chemical C that is produced? Well, if you remember, there's a law called the law of conservation of mass, which tells us that before and after a reaction or any process, mass is neither destroyed or gained, meaning that the mass will stay constant before and after a process. So before we have 15 grams and after we have, 3 grams plus 5 grams is just 8 grams. So wait, let me do that in a different color because we want to show the combination of the two. So 8 grams. So where did the 7 missing grams go? Well, it probably went to chemical C, since that's the only other thing that it could be, since A can decompose into B and C. So if we have A and B, C is our missing component, and that must be where the missing mass is. So we have to subtract 15.00 minus 8.00 in order to get the mass of chemical C. And we get that the mass of chemical C is 7.00 grams. And that's our answer. So let's move on to our next question. Is mass conserved before and after the reaction? So this is a reaction that converts this chemical called methane, and this chemical, oxygen. Ooh, I spelled that wrong. Oxygen. And these two combine to form carbon dioxide and water. So you may have heard of all these chemicals at one point in your life, and if you haven't, that's fine, because you will learn that in a future video. So don't worry about naming these chemicals and converting them into their names. Just worry about what the question is asking. The question is asking, is mass conserved before and after the reaction? So I'm going to clear the ink, and let's see if mass is conserved before and after the reaction. So in other words, are the number of atoms on both sides the same? Because remember what I said about the conservation of mass is that before and after, the amount of stuff or the amount of mass stays the same. So in this case, we're not using numbers, we're using atoms. So on this side, we have 1 carbon atom, 4 hydrogens, and 4 oxygens. And on this side, we have 4 oxygens, 4 hydrogens, and 1 carbon. So if we group these up, because it's getting confusing, we have the same number of atoms on both sides before and after the reaction. So mass is conserved, so yes. And that's the end of this video. And in the description of the video, I put down the lessons or videos that correspond to each question that is found in this test. So I hope you have a nice day, and I hope you learned a lot.